In this lesson, we will learn how to use Python code to implement the simulation that we talked about in the previous lesson, namely flipping a coin multiple times in a row, and after each coin flip, implement the procedure that we developed to detect whether it is biased or not. But before we dive into that topic, a brief minute about this first cell of code, which actually generates these figures of these distributions that we saw in the previous lesson. Now these show the histograms of a binomial distribution for a number of trials, which in this case is a number of coin flippings, and a probability of success for the underlying coin. Now generating the actual numbers for these histograms is not difficult at all, and we already did so in chapter 5. In effect, we're just generating populations according to a binomial distribution. To do this, we need a couple of numbers. The first one is the population size, which is the number of random points that we want to generate. The second one is the number of trials. In our example, the number of times that we want to flip a coin. Then the third parameter is the probability of success, or the underlying probability of the coin showing up heads. Now this can be a number between 0 and 1, and in this case we take a fair coin, so we have 0.5. Then the binomial distribution itself is generated by numpy.random.binomial, and we give it our parameters. And the rest of this cell is basically just all used for plotting. And the more difficult part is to get these percentages above each of these bars. But I will leave the exact details for the corresponding video on the Code for Data Science YouTube channel. So we can go straight ahead to the code cell where we actually make these very nice simulation plots of our coin flipping experiments. Remember, the code that generates these types of graphs. So let's see how we can do this. The first step will be to define upfront the two parameters that will determine the setting of our experiment and thus our simulation. The first parameter is the number of coin flippings that we want to simulate, and thus the number of trials in our experiment. The second parameter is the fundamental probability of the coin that we are simulating. It is the probability of our coin to show up heads. In this case, we take 0.5 to represent a fair coin. Now these few lines of code are there to validate the values of our parameters, namely that the number of trials, capital N, should be larger than 0, and that P, our fundamental probability, should be between 0 and 1. And if one of these two conditions is not met, then of course the simulation cannot be run and we get an error. Then the next step is to initiate some Python variables that will either change during our simulation or in which we will collect our results. Now the variable heads will be a number representing the number of heads that we got up to that point in our simulation. The same for the number of tails. Then outcomes will be initiated as an empty list, and in it we will collect the specific outcome for each flip. So heads, tails, tails, heads, and so on. Then in the next list we will collect the binomial probabilities, meaning the probability of getting exactly that many number of heads after a larger number of flips. Basically, these are the percentages that are above or on top of the bars in the histograms that we saw in the previous lesson. And then the p-values list will of course collect the p-value after each flip. So at the end of our experiment, all of these lists should have a size of 100. And then the entire simulation happens in this one for loop. So for each I in range n, meaning for each flip in our series of 100 flips, we do the following. The first thing that we need to do, of course, for each iteration in our for loop is to simulate a coin flip. And we can do so in the following way. We first generate a random number from a uniform distribution function between 0 and 1. So this could be 0.43 or 0.78 and so on. Then we check whether this random number that we generated is smaller than the probability for the coin turning up heads, which is what we defined before. If our random number is indeed smaller than, in this case, 0.5, then this flip will be true. If this random number is larger than 0.5, then this flip will be false. Now, because in our specific case right now, this probability is 0.5, and this random number is generated from a uniform distribution, then this flip will be true in 50% of the times and false in 50% of the times. So how do we now translate this true or false variable flip into getting either heads or tails? Well, we can do so in the following way. If flip is true, what we then do is that we define it as being heads. This means that we take our heads variable and we add 1 to it. Because remember, we initialized it as 0, and each time we get heads, then we just add 1 to it. So it represents the number of heads that we got in our entire experiment. Now, because the coin turned up heads, we of course also need to append this to our list containing all of the outcomes of our experiment. So we just do outcomes.append and we put an H for heads. Now, if on the other hand, our flip parameter is false, then we consider it being a tails. And thus we take our tails parameter and we add 1 to it and we append to our outcomes list T. So let's see how this now works with this probability of success. In this particular case, our probability of success was 0.5, so a fair coin. This means that in 50% of the times, this number will be smaller, and thus our flip will be true, and thus we have heads. But in 50% of the times, this random number will be larger, and thus this variable will be false, and then we get into this one. So we have tails. So let's now take the extreme scenario where the probability of our coin turning up heads is 100%. This means that this parameter here is exactly equal to 1, and therefore this randomly generated number will always be smaller than this number, and thus this inequality will always be true and flip will always be true for each of our coin flips. And therefore for each of our coin flips and appending H to our outcome list. And of course the other way around, if this number is 0, then this will never be satisfied, flip will always be false, and we will always end up in the tails scenario. And this is how we simulate a single coin flip where we can determine the probability of this coin turning up heads. Now, once for each coin flip we have either heads or tails, we need of course to compute the probability and the corresponding p-value. And that is what we will do next. So we define a variable, and this line here allows us to compute the probability of getting this number of heads out of this number of flips, because the number of flips will always be the number of heads plus the number of tails that we got, and our fundamental probability of our underlying coin. Then this probability we simply append to our list containing all of the probabilities for each step in our coin flipping experiment. And then we get to the procedure of being able to detect whether the coin is biased or not. And this boils down to computing the p-value at this point in our experiment, giving the null hypothesis that we have a fair coin. So the p-value, as we did many times before, is computed in the following way. We have stats dot, and then we take the binomial test. Now this is a statistical test, the same way as we saw and with the same reasoning underlying it, but now specifically in the case of a binomial distribution. So what are the parameters? Well, the number of heads that we had up until this point in our coin flipping sequence. Now the total number of flips is again the number of heads plus the number of tails that we got. Then the third parameter determines the null hypothesis. In this case, we want to have a null hypothesis of a fair coin. And thus, the null hypothesis value is that the probability of success of our coin is 0.5 or 50%. And then the fourth parameter indicates that we want to look at the extreme values on both sides of our histogram. Think back about the reasoning of our statistical test. And thus we compute the p-value for these parameters. And then we append the p-value to our p-values list, such that we get a list of p-values which tracks the p-value after each flip in our experiment. And then we are completely done with the simulation. We simulated a coin flip, and we implemented the procedure of trying to test whether this coin is biased or not. And all of the rest of this cell is just plotting the outcomes and printing the results. So the first print that we do is of course just the number of heads that we got after 100 flips and the number of tails that we obtained after 100 flips. And then we create a data frame which allows us to track after each flip a number of statistics. So after each flip, we want to know what the outcome of that specific coin flip was. We want to know the p-value at that point in our experiment, and we want to know the probability of getting exactly that number of heads given the null hypothesis also at that point in our experiment. And then we display both the beginning of our experiment, so the first 10 rows of this data frame, and the last 10 rows of this data frame. So let's already scroll down and look at these results. So if we scroll down, then we see indeed these results. In the end, the coin turned up heads 48 times, and it turned up tails 52 times. And of course, the sum of these two will always have to be 100. So let's now look at our experiment and compare these values for the first 10 flips. The first flip, we got a tails, and the p-value is of course 1, because we don't have any preconceived notion, and the probability of getting 0 heads after one flip is of course 50%. Now then we flip again and we get heads. The p-value remains unchanged, and the probability of getting 1 head after 2 flips is again 50%. And we then see how this evolves. Each time we flip, we get an outcome. Each time we compute the p-value, but at the start of our experiment, because we see that heads and tails are roughly equally distributed, our p-value remains 1. However, we see that our probability of getting exactly this number of heads after so many flips actually diminishes. And this is the phenomenon that I talked about earlier, where the most likely outcome for an increasing number of trials will always be the middle value, meaning equal number of heads and tails. However, the exact percentage of this likelihood will decrease, because of course we have more possible outcomes if we have more trials, and 100% needs to be distributed over a larger number of outcomes. So let's now look at the end of our experiment, the last 10 flips of our 100 flips. Now we see, of course, again the outcome. The p-value will have changed, and the probability is ever getting smaller, because of course we're getting more and more possible outcomes. Now if we look at the p-value, we see that it is very, very large. And again, this p-value represents the null hypothesis. Or in other words, what percentage of possible values under the null hypothesis is more extreme than the one we observe. And in this case, that is always more than 50%. So no chance that we detect this coin as being biased. So of course, these are just numbers in a table, but we want of course to have this nice figure, which basically shows the same result. So how do we now plot this figure? Now, I won't go into the details of it because it's quite elaborate, and I will leave that for the corresponding video on the Code for Data Science YouTube channel, but just observe the following. What we first do is define two lists that translate our outcomes list, which again is this list of H, T, H, T, T, H, corresponding to heads and tails, but now translate it to other words, which will be useful in our plot. In the first line, we translate these H's and T's to greens and reds. And of course, this will correspond to the bar color of the bars that we will put on our figure. And then in the second line, we will translate our outcomes list with the H's and the T's to a numerical list with 1s for H and -1 for T. And this will of course be the height of each bar corresponding to heads or tails. Then we use these lists to indeed plot our bars, which corresponds to heads being a green up bar and tails being a red down bar. And then the line for the p-value is plotted in this line, where we have numbers from 0 to n, our total amount of trials, on the x-axis, and the actual p-values on the y-axis. And then we plot the horizontal red line at a p-value of 0.05, which of course represents the level at which we can say that we can detect the biased coin with 95% certainty in this line right here. Now, this piece of code will make it so that if we cross this line, this horizontal line, then there will be some extra elements added to this graph. But we will see that once we actually get such a scenario. And that will be all of the code required to make such an elaborate simulation of coin flipping and generate the corresponding figure that entails a lot of information. Now we can of course scroll down, and the first thing that we can do is just to run this cell over and over again. And then again, as always, we see that we get different results for each run. Now this of course reflects the fact that we're still dealing with random numbers and statistics. Each time we redo an experiment, we will get different results. And the same is true for our graph. If we run this cell again, we will see that each time we will get a different graph. And in this specific run of our experiment, we see something very nice happening. In fact, this is perfect to showcase this link between our p-value, the blue line, and these bars, which represent the outcome of each individual flip. We see that we start with tails, then heads, heads, tails, tails, heads. And so after 6 flips, we have an equal number of heads and tails, 3 heads and 3 tails. But then something very strange happens. We see that we get tails, then tails again, tails, tails, tails. We get 9 tails in a row. Now this is very suspicious for a fair coin, because we expect an equal number of heads and an equal number of tails, roughly. However, at this point, the tails are just racking up. Now correspondingly, after each subsequent tails, the p-value plummets even further and further, because at each tails that comes up, it becomes less and less likely that this is a fair coin, and our skepticism should rise really fast. But then just when this blue line is about to cross this horizontal red line, meaning that our p-value drops below 0.05 and we have to reject the null hypothesis that this is indeed a fair coin, our coin turns up heads, which is this green bar here. And correspondingly, our p-value needs to adapt and just increases a little bit. But then of course we get 8 tails again and our p-value drops again. But then we have 4 heads in a row, again equalizing the number of tails and the number of heads that we have up to this point. And thus our p-value rises correspondingly. And it is in this way that you can see that this p-value really tracks the outcome of our individual coin flips. Now if we run this experiment over and over again, then we each time get a different result. So let's see if we can get a result where we actually go below this value of 0.05, which is indeed the case right here. So we see that in this first number of flips, we get a larger number of tails than we get heads. And this is not normal for a fair coin. And thus our p-value drops correspondingly. And just when it was already very low, we get a lot of tails in a row. And this of course pushes our p-value below this threshold line of 0.05. And here you can see the extra elements added onto this figure once our line drops below the 0.05 line. We see that we have this happening at flip number 28. So at this point, after 28 flips of our fair coin, we still have to reject the null hypothesis and we have to conclude that this is not a fair coin. Now, of course, this conclusion is wrong, just to be sure. But still, if we follow the right statistics, we have to make this conclusion. Because given this set of outcomes for a coin flip, we have to conclude that it is not a fair coin, or at least it is very unlikely to be a fair coin. In fact, after flip 28, we can conclude with 95% certainty that this is a biased coin. And we find ourselves in this 5% of cases that our procedure results in the false conclusion. However, we can also see that if we keep flipping coins and continue our experiment nonetheless, that the p-value rises again, crossing this line of 0.05 again, and indeed rises all the way up to a very normal value again. And that is of course because right after that we had a lot of tails from our coin flip, the coin turns up heads a lot of times. And this again restores this equilibrium between the number of tails and the number of heads. Now, of course, we can do this experiment again and again, and we see that most of the times we indeed do not cross this line. And our procedure makes the correct conclusion that this is indeed a fair coin. Now, because at this point we have our simulation ready and we really understand this graph, we can change some parameters to get different scenarios. And this really shows the strength of this simulation. We can see how our procedure does in different scenarios. For instance, if we have a lot more trials, if we flip the coin many more times, or if we have a much more biased coin, or anything else that we can think of. And that is what we will do in the next lesson.